Before ending this section, we need to discuss an important physical consequence of alloying, which is alloy disorder. When we create an alloy such as A sub x, B sub 1 minus x, atoms A and B are randomly distributed throughout the lattice. Because different atoms have different atomic potentials, the periodic potential of the crystal becomes locally non-periodic. This produces fluctuations in the crystal potential, as schematically depicted using solid lines in this figure, as shown. And it is denoted by U sub real as a function of position vector r. So the actual crystal potential fluctuates from site to site, depending on whether that site is occupied by atom A or atom B. These fluctuations act as a scattering potential for charge carriers. This means that electrons moving through the crystal experience a random variation in potential due to the random arrangement of atoms in space. This is called alloy scattering. On the other hand, using the virtual crystal approximation, we may replace the random potential with an average periodic potential using this formula, where the subscript VCA stands for virtual crystal approximation. This means that each lattice site is treated as if it contains a virtual atom whose potential is the weighted average of U sub A and U sub B, where U sub A is the atomic potential of atom A and U sub B is the atomic potential of atom B. Because this averaged atom is positioned at every lattice site, the resulting potential becomes periodic again. So by using the virtual crystal approximation, the random potential is replaced by an average periodic potential shown in the lower right, where the combined solid and dashed lines form the average virtual crystal potential. However, in the real material, the potential fluctuates around this average value. So in the figure shown here, the shaded area represents the difference between the real potential and the average virtual potential obtained using the virtual crystal approximation. So the fluctuations in potential are visualized by these shaded areas in this figure. They lead to electron scattering, reduced carrier mobility, and additional broadening of electronic states. So while alloying allows us to engineer band gaps and lattice constants, it also introduces disorder effects that influence carrier transport.